Good morning, ladies and gentlemen. A force is required to keep an object from moving in a straight line path.
That's just Newton's first law. An object in motion at constant velocity in a straight line path will remain in motion unless acted on by an outside force.
It really rolls off the tongue, doesn't it?
Yeah.
Okay. So we said a force is required to keep it from moving in a straight line path. I'm going to go ahead and start by rolling this in a straight line path. A force is going to be applied. And then as it comes out the other end...
Oh, do that again.
Oh, nice.
Strike! Notice it goes in a straight line path when it comes out. How come it wasn't going in a straight line path inside?
Well, there's a force being applied.
What's the direction of the force being applied? Do that again. It's going around in a circle.
Well, it's going around in a circle. Okay. So we have a slide for that. So the metal thing was applying the force, keeping it from going in a straight line path. If the path followed is circular or an arc, which we had, there is a centripetal force keeping it on the path. Okay, so the metal thing is providing a centripetal force. What's the direction of the centripetal force? Well, let's take a look at my contraption we have here. These are little fishing bobbers.
In water.
In water. And this is going to act just like our accelerometer. So the fishing bobbers, pretend like they're like the bubble.
They'll show the direction of the acceleration.
And what do we have here? What direction is the acceleration?
The bobbers are going toward the center.
Towards the center.
So if the acceleration is toward the center, what does that say about the net force?
That means that the net force, or the centripetal force in this case, is also towards the center.
Sweet!
Sweet! Where's what else? There we go. Okay, what provides the centripetal force for a twirled stopper? I forgot. I think it's up right. I think I want to. Yeah, there we go. What provides the centripetal force for? Don't hit anything here. For my twirling stopper.
Well, it's the string.
It's a string, right? Like, go the string and whoop. Okay.
Whoa.
And there we go. And it goes bonkers. Ding, ding, ding.
And so the string provides the force on the stopper, and you're pulling on the string. So what is that force called in the string? It's the force of tension. That's it.
Yeah. Okay.
It's the force of tension in the stopper.
So it's almost like
in
the
string.
force and tension and the centripetal force in this case are like the same thing.
Is there a slide for that?
Oh.
Nope. No, there's not.
Is there a slide for that? Okay, here we go. Let's go ahead and bring out Olga Kuzenkova.
Kuzenkova.
2004 Olympics women's hammer throw. First place.
Look at those lats. Can you say anabolic steroids?
Kuzenkova stepping into the ring for her third effort. Too many times she's seen other athletes come up with a great
She's got the hammer, which is a shot put on the end of a cable around. Wow!
And on her third round throw, she
Damn!
even further.
Oh, that's a scary looking person. I want her on my side in a fight.
In these games.
Why is the ball going around in a circle?
What's going on here?
What's providing the centripetal force?
Russians, especially in the throwing events.
Oh yeah.
Third throw.
Boom, 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 boom. Boom.
In other words, why is our stopper going around in a circle, right?
It's because it's the same thing. It's we can't throw the hammer here in the classroom. Things would get broken.
Yeah.
Not that we could, but
So the what's it called? The hammer, the ball thing?
it's called a hammer throw.
So the hammer throw, it's going
It's
around
like a
circle.
shot put on the end of a cable.
There you go. And it's going around a circle because of the string or the rope or whatever that force of tension is right there.
That's right.
Okay. Oh, practice roll.
A hammer thrower spins a mass on a cable 7 times in 5.85 seconds. What's the tension? What's the force of tension in the cable?
257 kilograms. Another day in Miss Moore's classroom where it's really cold.
Oh, I'm telling you.
But don't worry, tomorrow will be fixed, you guys. 215 meters.
I have no idea when they're going to see this. This could
Probably
be
a month from
January
now.
when they see this.
Oh, it better be fixed by
But on
then.
November 10th, the temperature in Fahrenheit in this room at this point at 7:30 in the morning is 58 degrees Fahrenheit.
You guys want to know the only reason Mr. Boykin knows the date?
That's right. He's old and retired.
He's retired. Okay.
Semi-retired.
So let me just get my information here. So I've got the mass, I've got the radius, and I'm gonna go ahead and calculate my my T first. Oh, I forgot to put seven rotations.
So 5.85 seconds for 7. We need the time for 1. That'll give us the period.
Yes. So it's gonna be 0.836. I'm gonna call it 0.84. 0.84 seconds per one rotation,
Yeah,
one
that's-
revolution.
Yeah.
Okay. So let's see. What am I trying to find here? The force of tension.
Force of tension. Well, the force of tension provides a centripetal force, right?
Yeah. So it should be mass times like that, right?
Centripetal acceleration and centripetal. You've got it over here on the board.
Oh yeah. Okay. So let's go ahead and do this. So my centripetal acceleration is going to be 4 pi squared r.
Because we don't know the velocity, we're going to use this 4 pi squared r over t squared.
Yeah. T squared. Okay. 0.84 seconds per revolution squared. And let me just go ahead and get that answer real quick. So I've got 4 pi, that's a 2. 4 pi squared times 1.215. I get that answer. I'm going to divide it by, what is it, 0.84 squared?
Yep.
Okay, I get 67. Let's just call it 68. Okay, so 68 meters per second squared. And that's going to go down here. So my mass was 7.257 kilograms times my acceleration 68 meters per second squared. And
That's going to be a lot of newtons.
it sure is. Here we go. So since
No wonder she's got such big muscles.
57 times 0.68. Oh, I did it. Oh, I did that wrong. Not 0.68. 7.257 times 68, not 0.68. And there we go. 493.
493 newtons. So she's got to hang on with an average force of 493 newtons. Damn!
Dang, that is a lot.
That's a lot.
Okay, so my next slide here. You guys ever seen one of these? So I think they still have them at the fair. I don't think they've gotten rid of them yet, but it's those. It's the ride that when you get in it, it starts to spin really fast.
There's a door in it
a
where
door,
you
yeah.
go in and you stand on the floor and there's carpeting along the walls that increases the force of friction.
Yeah, you just stand in front of the wall and then it starts to spin.
And then after it spins for a while, the floor drops out from under you and you're left pinned to the wall.
And you look like this.
Now what would happen if those walls broke?
If the walls went away, if the walls broke, no longer, they cease to exist.
Newton's
you just
first
go
law
flying, right?
would say you'd go flying outwards. That's right.
Yeah.
It's just like the stopper on the string or the shot put or on the hammer throw.
Okay. What provides the centripetal force when a car goes around a circular corner?
Well, what's between the car and the ground?
The road, right?
Yeah,
And then
the tires.
The tires. And what do we have some sort of something going on there.
And it is
Ba-ba-dum!
force of friction.
Force of friction. And we know how to calculate the force of friction. mu times the normal force. Yeah, pretty self-explanatory. Notice how the centripetal force equals the force of tension equals the force of friction.
Depending on the situation. Here,
Yeah.
what's making the car go around a circle? The friction between. And this is why wet roads are dangerous, because you have a smaller coefficient of friction when the road is wet, and
Smaller.
you can't go around a corner as fast.
Okay. And what provides the centripetal force when an airplane makes a turn?
When an airplane makes a turn, they have to tilt over like that. It's called banking. That's right, they bank over.
So what's going on here? It says the component of the lift force towards the center of the circle. Okay, so we have a lift force when an airplane turns. And,
Perpendicular to the wings.
and so then we can break that lift force down into its components, right?
Yeah, uh-huh.
We have the vertical component, which opposes gravity.
It's going to be the same, but equal and opposite.
And then we have the horizontal component.
Yep.
And the horizontal component is what causes that.
It provides a centripetal force.
Yeah, that centripetal force. Boom. Okay. What provides the centripetal force for the moon going around the Earth?
Oh, I remember we talked about this just the other day.
Yeah, we've been talking about this all week. So this is gravity. We know this. The gravity is what provides the centripetal force for the moon going around the sun, keeping it in orbit. Boom! There it is. In all its glory.
Now, if you look at these, can you imagine solving for a variable?
It's a lot of work.
Yeah, there's worse things.
Yeah, we could do it.
There's worse things like coming into this room here at 6:45 in the morning and have the
At 59
water being
degrees.
frozen.
Yeah, so if you want to solve for this, you just get rid of that. If you want to solve for this, you just flip everything over there.
Let's practice some of this.
Oh, yeah, should we?
Were there some homework problems?
Homework, page 138, numbers 16, 18, and 24. Put what we just talked about into practice. Go fight, win. You guys got it.
By the way, challenge, if you want to try number 15 as well, that's the one with that fair ride, the rotor thing. So
Give
if you
it a
want to do
go.
number 15 too.
Yeah.
But you
do
don't
it.
have to.
Only if you want to.
All right.
Okay, go.